Hi, welcome to Did the DONuT experiment discover the tau neutrino? Part 1. This video is the first in a two-part series. Here, in Part 1, I'll argue that DONuT did, in fact, discover the tau neutrino. In Part 2, I'll argue that they actually didn't. It's possible to make these two arguments because DONuT was the first experiment to directly observe the tau neutrino, but we pretty much already knew that it existed. So DONuT stands for Direct Observation of New Tau. It was located at Fermilab. It was experiment number E872, and it collected data in 1997. They published their initial results in 2001 and their final results in 2008. Here are the references for the two DONuT papers. You can also find these in the video description below. DONuT also needed to rely on the results of other experiments, E531 at Fermilab and Chorus and NOMAD at CERN. Relevant references are included here and in the video description below. Now, there are some other videos on this channel that might be of interest if you want some background info on the tau lepton or the tau neutrino. You might be interested in the videos Discovery of the tau lepton, the lifetime of the tau lepton, and how can the measured number of neutrino species be 2.9963 plus or minus 0.0074. Additionally, you might want to check out the videos in the Understanding 5 Sigma playlist. The background information in these videos will also be helpful when we get to Part 2. Okay, let's start with a few points about the standard model of particle physics. In the standard model, we have 6 quarks and 6 leptons, the gauge bosons that transmit the electromagnetic weak and strong forces, and the Higgs boson. In this video, we're going to be focused on the tau neutrino. Now, the quarks and leptons are arranged into 3 families. These families are related to how the quarks and leptons interact with the W boson, one of the mediators of the weak force. For example, the electron can interact with an electron neutrino and a W, and a down quark can interact with an up quark and a W. I should include a note here for the physics students. I'm ignoring the effects of the CKM matrix in this discussion, so this is slightly oversimplified, but it will work for our purposes here. The interaction that we'll be most interested in is the interaction between a charged tau lepton, a tau neutrino, and the W. Okay, let's look at 3 particle physics processes involving the tau neutrino that will be important for understanding what DONuT did. Okay, the 3 processes relevant for DONuT that we're going to look at are, first, Meson decays involving tau neutrinos. This is the main way that DONuT produced new taus. Next, interactions between tau neutrinos and nucleons, which can produce tau leptons. While a tau neutrino is essentially invisible, a charged tau lepton is not. If a tau neutrino interacts and produces a tau, the tau can be seen in a detector, and this is relevant for how DONuT observed tau neutrinos. And lastly, decays of the tau lepton. Tau leptons can decay in multiple ways, but all of these decays contain a tau neutrino. This is relevant for how tau leptons are identified by DONuT. I'll talk about each of these 3 processes, and we'll see each of them again when we go through the details of how the DONuT experiment worked. They're each a bit complicated, so I'll try to give the 1 or 2 sentence upshot of what you need to remember about them in order to understand what DONuT did. I should also note that DONuT produced both tau neutrinos and tau antineutrinos. I will sometimes casually refer to both of these as simply neutrinos, and I may refer to both positively and negatively charged tau leptons as simply tau leptons or taus. But for many of the processes I'll mention here, both are important. Okay, let's start with meson decays involving tau neutrinos. In a basic model of a meson, the meson contains a quark and an antiquark. Let's consider a negatively charged meson, which consists of a quark and antiquark of different types. That quark and antiquark contained in the meson can conceivably annihilate each other to form a W boson. And that W boson can disintegrate to a tau lepton and a tau antineutrino. This is shown in the diagram at right. If we read it from left to right, and note that we're using the convention that arrows are reversed on antiparticle lines. In this way, the negatively charged meson can decay to a tau lepton and a tau antineutrino. Now, compared to a lot of mesons, the tau lepton is pretty heavy. It weighs about 1.8 GeV. The 3 lightest quarks, the U, D, and S, are much lighter than this, and the mesons made of them tend to be very light, too light to decay to a tau lepton. So let's look at a meson that contains a C quark. It's quite a bit heavier than a U, D, or an S. A negatively charged D sub S meson contains an S quark and a C antiquark. It weighs about 1.97 GeV, so is heavy enough to decay to a tau lepton and a tau antineutrino. In fact, for each of these mesons that decays in this way, you get both a tau neutrino and a tau antineutrino because the tau itself decays, producing a tau neutrino. The decay of this meson plus the corresponding decay of a positively charged D sub S to an anti-tau and a tau neutrino are the primary way that DONuT made tau neutrinos and antineutrinos. Okay, that was a little complicated, but the upshot here is that charged D sub S mesons can decay, producing tau neutrinos and tau leptons. So, if you can produce D sub S mesons, you can produce tau neutrinos. And that is what DONuT did. Okay, next let's talk about interactions between tau neutrinos and nucleons, which are the protons and neutrons in the nucleus of atoms. We saw before that there was an interaction between a tau neutrino, and a W. We also saw an interaction between a U quark, a D quark, and a W. We can glue these two interactions together to make this diagram. If we read this diagram from left to right, we have the interaction where a tau neutrino and a down quark can turn into a tau lepton and an up quark. We can similarly write down a diagram that represents a tau antineutrino and an up quark turning into an anti-tau and a down quark. Now, the initial U or D could be inside a nucleon, which is a proton or neutron. When quarks are given a large kick, they tend to produce a shower of hadrons, where hadrons are the generic term for particles made of quarks and antiquarks and gluons. So, a high-energy neutrino or antineutrino can impinge on a nucleon, producing a tau lepton and possibly many hadrons. What we're interested in here is that the invisible neutrino or antineutrino gets converted into a charged tau lepton, which is visible and can be picked up by a detector. So the main point about the interactions of tau neutrinos with nucleons is that these neutrinos can interact in matter at a tiny rate, and a new tau can interact to make a tau lepton. And this is important because the tau lepton can be detected, and that's how we know that the neutrino interaction happened. Okay, but once the tau lepton is produced, it decays. So we need to talk about that. So a tau lepton can disintegrate into a tau neutrino and a W. The W then further disintegrates. It can disintegrate into an electron and an electron antineutrino. This gives the decay tau goes to tau neutrino, electron, and electron antineutrino. And the decay of a positively charged tau lepton is analogous. Just replace all of the particles in this diagram with their antiparticles, and you get the diagram for a tau plus decay. The W can also disintegrate into a muon and a muon antineutrino. Or it can go to quarks. Here, only the lightest quarks, U, D, and S, are relevant. All of the other combinations of quarks are too heavy to be produced in tau decay. The quark-antiquark pair that is produced will arrange themselves into some number of hadrons. So this produces the decay of a tau going to a tau neutrino and one or more hadrons. The simplest example is a tau decaying to a tau neutrino and a pion. The fact that the tau decays into other particles aids in its identification. DONuT looked for evidence of these decays to find taus resulting from interactions of tau neutrinos with nucleons. Okay, so just to summarize the points about the tau decays. We saw earlier that the tau neutrino interactions with nucleons produce a tau lepton, and so identifying this tau is important for knowing that tau neutrino ever existed. The tau lepton subsequently decays. It can decay in multiple ways, all of which produce another tau neutrino. Understanding these decays was important for identifying the taus in DONuT. Okay, now that we have those preliminaries out of the way, let's talk about what the experiment actually did. You might be familiar with the Tevatron accelerator at Fermilab. The Tevatron collided protons and antiprotons at two experiments, CDF and D0. You might remember that CDF put out a new measurement of the W mass last year. But that's not all that the Tevatron could do. It also sent 800 GeV protons to the DONuT experiment, located down here in the lower right-hand corner, not too far from the bison barn. Okay, let's give a schematic of the DONuT experiment. The 800 GeV proton beam is incident from the left. This beam hits a tungsten target, and this produces showers of hadrons. This gives a huge variety of particles, most of which are not useful for tau neutrino searches. Most of these particles stop in the subsequent shielding, shown here as a purple rectangle. But some of the particles that are produced decay, and some of those decays can produce neutrinos and antineutrinos of any variety, electron, muon, or tau. These neutrinos can invisibly get through the shielding, pretty much unaffected. Now, out of the huge variety of particles produced in the tungsten target, occasionally a positively or negatively charged D sub S meson is produced. We saw earlier that a D sub S can decay to a tau and its associated antineutrino. Also, we mentioned that tau leptons decay, producing tau neutrinos. So the D sub S decay will produce a tau neutrino and antineutrino, one directly and one through the decay of the tau lepton. So each D sub S that decays in this way produces both a tau neutrino and a tau antineutrino. This isn't the only way that tau neutrinos are made in the tungsten target, but it is the main way. Now, neutrinos are very weakly interacting, so these tau neutrinos from D sub S decays fly through the shielding, which stops most other particles which we aren't interested in. Other neutrinos and antineutrinos will also make it through. The only other particles likely to make it through the shielding are positive and negative muons. But these are identified and rejected by a veto system, so this is how DONuT produced a pure source of neutrinos. Once a tau neutrino makes it through the shielding, it can interact with a nucleon in the emulsion target through the diagrams we saw earlier. This produces a tau lepton and some hadrons. We're mostly interested in the tau lepton. It's the smoking gun signature that a tau neutrino was produced. So correctly identifying this tau lepton is really important. Now, this tau lepton decays, but it typically travels about 2 millimeters before that happens. The emulsion targets record tracks of charged particles with high precision, and the spectrometer measures particle energies and tracks and does particle identification. So the tau lepton can create a track which ends after about 2 millimeters. The tau lepton decays into one or more particles plus a tau neutrino. This tau neutrino flies off invisibly, but it carries momentum. This gives the other decay products of the tau lepton a kick. Now, those other products of the tau lepton decay can make tracks. But because some momentum was carried off by the newly produced neutrino, these tracks may show a kink relative to the track created by the parent tau lepton. So the ideal signature of a tau lepton is a short track plus decay products that display a kink relative to the tau itself. And this appearance of a tau lepton in the emulsion targets is what signals that a tau neutrino was produced in the tungsten target. Now we need to briefly discuss a complication, which is background processes. As we mentioned, other neutrinos, electron and muon type neutrinos, which we're not really interested in, can also make it through the shielding. If they interact in the emulsion targets, they can be mistaken for tau neutrino events. Sometimes these interactions will produce particles with a lifetime similar to that of a tau lepton. Then they can leave a short track and decay, closely mimicking a tau. The rate of these background processes must be estimated. Okay, with that, let's get to their results. DONuT published 2 versions of their results. Their initial results were in 2001, and their final results were in 2008. These two papers were on the same dataset, but between the two results they modified their analysis to pick up signal events more efficiently. In their initial paper, they saw 4 candidate tau neutrino or antineutrino events. The expected number from uninteresting background processes was 0.34 plus or minus 0.05. Additionally, the expected number if the standard model tau neutrino in fact existed was 4.2, right in line with what was seen. In their final paper, they reported seeing 9 events, with 1.5 expected from background. In the standard model, they would expect to see 10 tau neutrino events, again in line with observation. So let's take a look at those results and see how good the case for the tau neutrino was from their dataset. We can take the expected background and use the Poisson distribution to get a p-value for each of these results. We find that the events reported in the 2001 result constituted a 3.3 sigma observation, and those reported in 2008 gave a 4 sigma observation. Both rates were compatible with that expected from tau neutrino production. So this is evidence for production of tau neutrinos. It didn't reach the conventional 5 sigma threshold that particle physicists tend to use for defining discovery, a point that we'll return to in the second video. But there is one more important point. How do we know that it's new tau? So DONuT saw a particle that was produced in the tungsten target, invisibly traversed the shielding, and interacted in the emulsion targets to produce tau leptons. In the standard model, the particle responsible for such interactions is the new tau. But the SM also contains electron and muon neutrinos, and they would also be able to traverse the shielding. What if the electron or muon neutrinos had non-standard interactions and could produce taus? How do we know DONuT saw a third neutrino and not unexpected interactions of nu E and or nu mu? To determine that their results were evidence of new tau and not non-standard nu E or nu mu interactions, DONuT needed the results of other experiments. Enter NOMAD and Chorus at CERN and E531 at Fermilab. These 3 experiments aimed muon neutrino beams at targets and looked for evidence of production of tau leptons. They saw no evidence of a signal and put limits on the interactions of the muon neutrino with the tau lepton. The beam also had a small electron neutrino component, so they were able to set weaker limits on the interactions of the electron neutrino with the tau lepton. The results from NOMAD and Chorus were stronger than the previous results of E531. They indicated only a small component of DONuT events could possibly come from non-standard nu E or nu mu interactions. Including this possibility would decrease the significance of DONuT's results, but not change their conclusions. Okay, let's look at what's coming up in part 2. We saw here in part 1 that DONuT saw evidence for the new tau. It was the first experiment to produce the new tau and see it unambiguously interact in a detector producing tau leptons. Their evidence didn't meet the conventional 5 sigma threshold used in particle physics. In part 2, we'll argue that they didn't discover the tau neutrino, but not because their excess was less than 5 sigma. There were other, arguably less direct experimental results that, if taken together, had already nailed the tau neutrino down. And because DONuT was corroborating previous results, requiring 5 sigma would arguably be overkill. So, stay tuned for part 2.